Okay, here we go. So before we get into the math, just real quick, I want to remind y'all that two things. First of all, I believe that the ad drop deadline is tonight. Is that right? I don't know. Y'all may know better than I want to say it's tonight, but I'm not sure. Anyway, it's coming up soon, so heads up. Don't assume that I have the date and time right. I have no authority on that. But I want to say that it's tonight. So two relevant points there. Think it through. Make sure you either are enrolled if you'd like to be and are not enrolled if you do not want to be, etc. But also, hopefully and presumably, that means that tomorrow, Friday, our roster will be settled. The only reason that I haven't been taking attendance up to now is because the roster is in flux and it's just a nightmare of like people adding and dropping, and it's too much confusion. But once the roster is settled, attendance starts to make sense. So anyway, tomorrow's class will be the first class in which I will be counting attendance as part of your grade. And see the course grades section of the website for all the details. But the punchline, it doesn't count for much, but you'd be surprised how much of an impact it can make. Even it's only 3%, right? But the difference between, you can do the arithmetic, right? You can see that the attendance score, each time you skip class, it costs you just that little bit that really can make a difference in your course grade. Okay, all right. So starting tomorrow, attendance counts. Okay, so here's where we were last time. Reminder: in this course, my Math212 notes are these are the ones that are going to be the index for the course and determine the order that we do the topics, et cetera, et cetera. But very often I'll be using my Math219 notes where depending on my preferences, I kind of like the way I wrote it here a little better or something like that. It is a little bit more easy to read, I think, because it's not a scan of pencil written notes. This is digitally written in the first place. So anyway, this right here we're looking at my Math219 notes, but this is alternative version of what's in the 212 notes. Okay, last time we talked about this idea that if you represent a plane by way of a point in the plane and a vector perpendicular to the plane, right? Then the result of that is that the equation for the plane is this right here. It's a very simple, easy to remember little formula. Whatever that point is that's in the plane goes here. Whatever your in vector is perpendicular to the plane goes there. And keep in mind what an equation is. An equation is what I like to call a point tester. Right? If you have an equation and someone comes to you with a point and says, "Hey, is this point in the plane or is it not in the plane?" The way you decide is you take the point that you're interested in and you stick it right there, and then you ask, does the equation work? If the equation works, yes, it's in the plane. If the equation doesn't work, then nope, it's not in the plane. Right? So that's just a quick, I know you all know what an equation is, but it's important to actively think about it in those terms. And then, of course, you can write the equation of a plane in a different form. Okay, so all discussed last time. So here's an example. Now, when you see examples about lines and planes, very often there is a kind of what I'm going to call a puzzle aspect to the question. Namely, certain facts and certain methods and various tools that you have at hand, and the question is going to be, I've got some information about these things and I want to figure out other information about this stuff. And you've got to figure out how to use your various tools to strategically, cleverly get to the information that you actually want. So this is a nice starting example of that sort of thing. So we've got 3 points given, A, B, and C. And given those 3 points, well, first of all, let me observe that 3 points, as long as they don't sort of line up, 3 points will define a plane. Right? Random 3 points in space, again, unless they just happen to be right along a single line, something dumb like that. So this plane, the question that we want to resolve then is to find what is the equation of this plane. So notice I have some information about it. I want different information about it. And thus begins the puzzle. So the way that we resolve these puzzles is, you kind of think forward from what you have and backwards from what you need. So let's start by thinking backwards from what I need. I want the equation. In order to find the equation, sure would be helpful if I had the normal vector, the in vector, right? The thing that's perpendicular to the plane I'm interested in. Sure would be nice if I had a point in the plane. Oh, cool, I have 3 of them. Okay, so we don't need to worry about that part. We have 3 points to choose from that'll be just as good as, being the point in the plane. But I need to find a normal vector, apparently. Right? So that's working backwards from where we want to get. If I want the equation, apparently I need a normal vector. Working forward from what I have. Again, I have these 3 points. And what can you do with points in a plane? Well, I suppose there's a lot of things you could do, but check it out. An easy thing to do is to pairwise subtract, and that gives you vectors parallel to the plane. Okay, so I've done a little bit of working forward from what I have, a little working backwards from what I want, and now let's again just kind of think strategically. How can you get there from here? I have apparently 3 points in the plane and 2 vectors parallel to the plane. How can I use those, hopefully, to find a vector perpendicular to the plane? And you just have to kind of search in your mind for what tools do I have that do this? How do I find something that's perpendicular to the plane? Notice that means I need it to be perpendicular to these vectors parallel to the plane. I've got 2 vectors. I want to find something else that's perpendicular to both of them. Where have we heard that before? That's our cross product tool. Does that make sense to everybody? So now again, there's 2 things going on here. There's the actual computations and applying the specific tools that we have, but then there's the strategery, right? There's the how do I solve the puzzle? How do you connect the dots? And again, I kind of like the idea of thinking of it as you work backwards from what you want. I want the equation. The equation requires that I find a normal vector. And then working forwards from what you're given. I have points in the plane that allows me to make vectors parallel to the plane. So there you go. How are we doing? Is everybody? Yes?
Why are you using vector notation for the points?
Yeah, no, that's right. So you may recall, so one of the first things we talked about is that first day of class was points and vectors. While they are different, there is a natural correspondence between them. And so we conflate the notations because it's extremely convenient. And context will always make it clear which we mean, right? So for example, here, I've got this thing that I've called in, right? I've generated it as a cross product, but what am I doing with it? What I'm doing with it is I'm using this to define a direction. Right? And because I'm using it to define a direction, what I pretty clearly mean by this is I'm thinking about a vector, not a point. Does that make sense? Yeah. So it's a very convenient conflation, and it's a little sloppy. But I've been doing this for decades, let's not say how many, and I've never gotten a problem. I've never run into trouble with it. That's why I think it's a nice convenience. Yeah. All right. Okay, moving along. So let's see here. Neat fact. I just like pointing this out because it's a wonderful little shortcut. So keep your eyes out for this. You might find yourself in such a circumstance. And in fact, you're very likely to find yourself in such a circumstance. So if you have the equation of a plane, right? You know what the equation of a plane looks like. We just wrote it down. And hypothetically, if there are no y's in the equation, right? So notice here, there's 0 y's in that equation. In fact, it may have come to you with that term not even having been written down. If you just see ax plus cz equals d, right? just let me finish that. The amazing conclusion is that the plane that this represents is parallel to the y-axis. Shocking result. Very convenient to observe. Very convenient to observe. Just at a glance, there's no y's in the equation of this plane. And then powerful geometric conclusion about the orientation of the plane. Yeah, go ahead.
Is that only true for the y-axis?
No, this is just an example. But yeah, same analogous statement works for the x and z as well. Yeah. Okay, so let's just kind of think through why this is. Here's the argument. Here's the equation of the plane in question, again with the 0 y's. Notice that means that my normal vector, keep in mind that the coefficients are the normal vector. My normal vector is like that. And beautifully, that normal vector at a quick glance, right, noticing where that 0 is, I can see that that's perpendicular to the y-axis. Now you can either just eyeball that, right? Or if you want to see an algebraic confirmation of this, the vector that I can point in the direction of the y-axis very easily would be E2, namely 0, 1, 0, and you can just directly confirm for yourself that this vector and that vector are clearly orthogonal because the dot product clearly 0. Yeah. Okay, well, and then we're done because if the vector perpendicular to the plane is also perpendicular to the y-axis, now this is a geometric appeal, right? But it kind of forces this plane to be parallel to the y-axis. Everybody happy? Nice little observation, good little, as I like to say, a good tool for your toolbox. It'll come up here and there. It's very nice to have these tools right there on hand in your toolbox. Okay. All right. Next thing, I'm going to have to take a quick aside and talk about parametrizing lines. I haven't told you all yet what a parameterization is. You'll notice I'm switching back to my Math212 notes. There's going to be a lot of sort of switching back and forth. So a parameterization in general is something very different from an equation. Remember, an equation is a point tester. You come to me with the point. I test it with the equation. A parameterization is not. A parameterization generates points. You don't come to me with anything. A parameterization just creates points that are on the plane. But doesn't really work very well to test points. So it's a kind of they relate to lines in different ways. One of them tests points, one of them generates points. So there's a pretty easy formula for how to do this. It's not hard. If let's suppose that there's some line I'm interested in, and if I know a point on that line, and if I know a vector parallel to that line, then, this point, x naught, plus, and now let's take our vector parallel to the line and scale it. We'll multiply by any value of t. Whatever that value of t is that you multiply by your vector parallel to the line, the result will also be parallel to that line. And notice then that what this creates, let's see, blue plus purple, that always creates a point on the line, right? So you give me any value of t, doesn't matter. It's completely independent, just arbitrary. Any value of t, this will generate a point on your line. So it's what we call a parameterization. Everybody happy with that? All right. Now, how do you think about this? I mean, it is what it is, but it is also convenient to think of this t as being time. And if you think of t as being time, then this formula here effectively traces out the line. So when t equals 0, I'm here. When t equals 1, I'm here. When t equals 2, I'm there. It's like as time passes, 0, 1, 2. As the seconds tick off, I'm literally tracing out the line. I think this is a lovely little, metaphor. Is that the right word? But way to think about what a parameterization is doing. It's a very common choice. Think of t as being time. Just for the record, now, though, you don't have to. Right? All we really need t to do is just be there, right? Any arbitrary number, you don't have, it's not intrinsically that time, but very convenient to think of it that way. Okay. All right. Now, a quick observation about parameterizations. Turns out there's lots of them. It's not even that hard to see. You can confirm for yourself, for example, this point is generated by that parameterization when t equals 2. Right? And then notice that this point is on this parameterization when s equals -1. So each of these, let's say it this way, each one of these points is on both of these lines. That means that these are the same line. They trace out the exact same line. They just kind of trace out the exact same line in different ways. Right? They start at different points. This one here appears to be moving a little faster because every second that ticks off, I move by twice as much as every second that this ticks off. Right? So they're different parameterizations, but they are exactly the same line. So just make sure to be aware, parameterizations are not unique. But that's I don't even think of that as a bad thing or a good thing. I like to think of it as, I'm an optimist in some cases. I like to think of this as, hey, look at all the options we have for how to parameterize. Okay. All right. So suppose, though, that I have a parameterization, like so, and suppose that what I want is to turn that into an equation. Right? I have a parameterization of a line. I want to get an equation of a line. I have a point generator. I want a point tester. How do you, what's the sort of the process? And it's a real clever little move. The idea is this. You can take this vector parameterization here. It's written as a vector equation. Write that out in coordinates. That gives you this. And now let's ask the question, if someone came to me with a point, if someone came to me with an x and a y, what would be the right value of t for the parameterization to generate that point? And, well, that's actually a pretty easy question to answer. Just from looking at the x-coordinate, t would have to be that expression right there to solving that first equation. But here's the catch. T would also have to be that expression right there from solving the second equation. So if you come to me with an x and a y and ask me, is that point on the parametric line, t would have to equal to both of these values. And quick pause. Let's just think strategically. How could t possibly equal to two different expressions? And there's really only one way that's possible. It's only possible if these expressions are equal to each other. Does that make sense to everybody? So notice then what we have is an equation, right? So we have successfully turned a parameterization into an equation by a reasonable and meaningful argument. And you can turn this around backwards. If you have an equation in this form, or it doesn't even have to be in any sort of vaguely similar form, well, just set both of those things equal to t and then solve for x and solve for y. And that gives you a parameterization. Everybody on board? Very analogous argument, works in 3 dimensions. If you have a 3-dimensional parameterization, that gives you 3 equations, each of which tells you a value that t must equal to. how could t equal to all three of those things? Well, the only way t could equal to all three of those things is if all three of those things are equal to each other. Again, same clever argument. If t's got to be equal to three separate things, those three separate things can't be different. They all have to be the same. And so this is a different looking thing. You might not recognize this. This is not an equation. This is actually two equations. Or depending on your point of view, obviously that's got to equal to that as well. Or maybe this is three equations. Right? It doesn't really matter how you think of those terms. But anyway, this is nevertheless still the point tester. If you come to me with an XYZ, I can plug in the XYZ. All three of these better be equal. If so, it's on the line. If not, it's not on the line. Okay. Is everybody happy? All right. Yeah. Okay. So, here's another example, going back to the 219 notes. Suppose I want to parameterize a line. But I'm not going to give you exactly all of the information that you want. I'm going to give you a point that's on the line, and I'm going to give you a couple of planes. I'm going to give you that plane, and I'm going to give you this plane, and I'm going to insist that the line that I'm looking for, the line that I'm trying to parameterize, is parallel to both of those given planes. Right? So now again, we're in this weird situation where, okay, we have some information given, but I would need to solve for different information. And again, there's a puzzle aspect to this. Very routine, regularly, I'm going to kind of say always, just because in effect it might as well be, should always make a picture. It doesn't have to be accurate. Notice that this picture that I've made for that plane, that's probably not exactly what this plane looks like. It just needs to be figuratively accurate. So notice I did try to go to the trouble to make it look like this line actually is parallel to both of these planes. As is given. So that kind of thing, you want to be, representative of the relevant points, but whether it's actually right doesn't really matter in most cases. Okay. All right. So here's the big idea. I'm going to argue that these normal vectors I can pull straight out of the equations, as previously noted. Right? And now what do I need? Well, I need that vector right there. I need this v vector parallel to the line because that's one of the tools involved in parameterizing. So here's, me working backwards from the goal. And again, here's me working forward from the givens. Right? And now, so having done that and it not being immediately clear where else I can sort of immediately work forward, immediately work backward, now let's sit back, think strategically, look at the geometry of the picture, and I think I can persuade you that if these vectors are perpendicular to these planes, and these planes are parallel to this line and thus that vector, then there's kind of a transitivity, sort of, if you will, that this is going to have to be perpendicular to both of those. Now, again, that's a geometric appeal. You get very often in these questions, you have to have a geometric sense for how to connect those dots. And again, the pictures really help a lot. By the way, let me emphasize, the pictures help you to connect the dots, and it also helps your grader to see how you connected the dots and to see what you understand from the about the problem. So it's a double win to have a reasonably decent picture, a la what I've got here. Okay, and again, how do we do this? How do we find a vector perpendicular to two other vectors? Well, our old formula, the cross product, does it for us. Is everybody all right? Okay. Okay. Now, a quick warning. In both of the previous examples, I used what I'm going to call transitivity arguments, and I even said so here. I argued that these vectors are perpendicular to these planes, respectively. Those planes are parallel to this vector, and then there's, if this to that and that to the other, then you kind of draw a transitive conclusion, right? So, yeah, that fits the bill in this case, and there's also a transitivity in the previous example here, right? And the idea is that the plane is perpendicular to that vector, and that vector is perpendicular to the y-axis, and then you kind of think through again geometry and intuition about the geometry, and okay, so therefore the plane and the line have a concluded relationship. So when you have these transitivity-like arguments, be careful, because they don't all work the way, as you write them down on the page, what seems like it really ought to work, without, before you really think through the geometry, doesn't always work. So for example, easy example, this vector is parallel to that plane, and that same plane is parallel to that vector. But notice, it is not the case that the transitivity would imply that these are parallel. It just doesn't. They're not necessarily parallel. They're not necessarily perpendicular. They're nothing. There's no conclusion to be made. So heads up, right? You always think through the geometry and make sure that what you're claiming geometrically is actually valid. Now, there's too many different combinations of lines and planes and parallel and perpendicular, and oh my gosh. I'm not going to enumerate all such rules. I'm just going to say you should always think careful geometrically. And in this course, the rule is if you're right, then it's okay. But if you make a claim of this sort, that this and therefore those must be parallel, that's a wrong claim, and you'll lose points for that. Does that make sense? So your arguments have to be valid. Simple as that. So heads up, just make sure to always think through the geometry. Here's another counterexample. This plane P is perpendicular to this plane Q. And furthermore, that same plane Q is perpendicular to this plane R. But notice that P and R, no relationship. Maybe they're parallel, maybe they're perpendicular, maybe they're at some random angle as I have drawn here. No conclusion to be drawn. Is everybody happy? It's a dangerous little landmine to, if you think too algebraically, it won't be clear how this stuff works. You have to think geometrically. Okay. All right, moving along. Okay, so let's talk about generating a plane. How do I parameterize a plane? Morally, the same idea as parameterizing a line. You're going to have to give me a starting point in the plane. And I'm going to need a couple of vectors. I'm going to need a V vector. Come on, stylus. Here we go. Parallel to the plane, I'm going to need a W vector parallel to the plane. And I claim with this, if I have a point in the plane, two vectors, not parallel to each other, parallel to the plane, claim this is enough. And the big idea, not so challenging, I think, geometrically, is that I can look at multiples of the V vector, and I can look at multiples of the W vector, and following this formula here, A plus a multiple of V plus a multiple of W will get us to not only a point on the plane, but by making, whatever choices are necessary of these parameters, S and T, I can get to any point on this plane. Just by choosing S and T to make these green and blue vectors longer or shorter as needed, I can get anywhere I need to go. Does that make sense? Is it geometrically plausible? Yeah. Yeah. Uh-huh.
Wait, so is this one in R3 or?
Yeah, this is in 3 dimensions. Yep. Right. Okay, so that's parametric plane. Now, real quick, let's address the weirdness. Wait a minute. We've got 2 different parameters here. Which one is time? Right? When we were talking about parametric lines, it was nice to think of the parameter as being time. Yeah, you can't here. I mean, you can't have 2 independent notions of time. That would be a really fun sci-fi movie. I would totally watch that movie, but it's not, I don't know how to make real actual sense out of that. Right? So here you have to sadly just think of S and T as being arbitrary parameters and kind of abandon that whole time point of view. Okay. Alrighty. Okay, so quick example. Again, arbitrarily, let's suppose that I'm given 3 points. Those 3 points define a plane. There is a unique plane containing those 3 points. Now again, let's assume that the points don't line up in some annoying way. How would I find a parameterization of this plane? Well, again, think about what you have, think about what you need. It's really easy to take what we have and make these vectors here parallel to the plane, which, as we just saw, are exactly what I need. I mean, sometimes the fish just jump in the boat. Exactly what I need to, wrong color. Exactly what I need to parameterize that plane. Everybody happy? Yep.
Why does it have to be B minus A?
Oh yeah, no it doesn't. It could, yeah, you've got a lot of options on how you do this. Now this was just a for example, but if you would like, if I can get my stuff erased here, if you would like, you could do, A minus C and, B minus C. That would work just fine. Yeah. Totally. Alright. And again, parameterizations of planes not unique, right? So, all right. Okay, so here's another category of question. I'm going to call these distance problems. And so there's a bunch of different categories of these. How do you find the distance from a point to a line? Or how do you find the distance between 2 parallel planes? Or how do you find the distance between 2 lines that in space that are not parallel and don't intersect? We call those skew lines. So there's a distance between them. How do I find that distance? This kind of thing. So all of these are what I call distance problems. And I'm going to just show you some neat little clever ideas that other people have thought of that you can take advantage of for yourself as well. And the tools that we use to answer these problems can be used to answer other kinds of questions as well. So again, keep in mind, this class, what we're doing in this course is I'm not showing you a bunch of algorithms to memorize, right? I'm showing you various tools and how to use them, but you're going to be, I'm going to show you how to use an electric sander and how to use a circular saw and how to use a miter saw. You're going to be building your own bookcase though, right? So what we're doing is practicing how to use the various tools, but your challenge is going to be how to use those tools to accomplish tasks. Okay. All right. So here we go. If I have a point on the line, and if I have a line, but in particular, let's suppose I have a parameterization of the line, and of course I can infer from a parameterization a point on the line and a vector parallel to the line. So that's given too, in effect. And notice then what that means is, I've actually got then this vector just by subtraction. That's what I'm going to call W. Okay, let's see here. I can also use the idea of a projection. Oh, whoops, I already used that color. I can use a projection to find that vector, right? And, well, the projection, if I subtract that from the purple vector, that difference is this vector, whose magnitude is the distance that I'm looking for. So it's just kind of a neat little strategy for, again, how this is the puzzle trick on this kind of question. Right? This is one of two, but anyway, this is the first trick that I'm showing you for your toolbox. Now, here, same question, different trick. This one's arguably more clever. I'm not sure if it's an easier answer, but it is arguably more clever. This is another mathematical bank shot. I'm going to get to the thing that I'm interested in by computing something I'm not interested in. It's weird how this works out sometimes. So, given the point, given the line, which means I have the x naught and the v. Right, here's the big idea. I'm going to imagine this parallelogram. The initial question did not have anything to do with this parallelogram, but I'm going to think about it anyway. I'm going to compute its area. Big picture strategy is I'm going to compute its area two different ways, and we've seen this several times already, or at least a couple of times. We're going to compute this thing two different ways, and in doing so, notice that I'll be able to relate the distance I'm interested in to other things, thus giving me an equation I can then solve. Everybody see the big picture idea? We'll talk about the details in a second here. But strategically, very clever idea. Wish I thought of it. Somebody showed this to me. But sometimes computing something you don't want, but that involves the thing you're interested in, is the foot in the door that you need. So anyway, let's talk about the details. How do I get this area? Well, one point of view is to say that it's green times orange, right? Just high school geometry. That area is green times orange, no problem. Now, alternatively, though, different way that I can find that same area. I knew I was going to do that. Okay, let's put this back. Another way to compute this same area is to observe that area is it's an area of a parallelogram in space. Where have I heard that before? That is the magnitude of the cross product of these two vectors. So the magnitude of the cross product, an old formula for area. Yeah.
Can you please explain the projection of V?
Yeah. So that's so it uses the idea of a component. Remember we talked about components? This is a great question, by the way. So this projection vector, I know its magnitude is literally the component, right? And then all I really need is to multiply that by a unit vector that points in this direction and a unit vector that points in the direction of V. It's another trick that we talked about, right? You take V divided by the magnitude of V. And so the projection has this as its direction, and it has the component as its magnitude, and you just multiply it. Yeah. Does that make sense? Is everybody happy with that? Okay. Yeah. So yeah, very often these solutions have, several little moving parts that, you kind of have to sort of assemble together. Yeah. All right. So yeah, really clever idea, but it does lead to a very handy dandy little formula. Looking at these two different formulas for area allows me to find a really simple formula for distance. Slick. Okay, how do we find the distance between parallel planes? I have two planes parallel to each other. There is this idea of a distance between them that, by the way, when you are talking about a distance between two objects, you do have to think through carefully, wait, what does that mean? When we say the distance between two parallel planes, I hope it would seem reasonable that we're talking about what we call the perpendicular distance, right? Because it's the only non-arbitrary choice for what that could mean. Okay. All right. So, wonderful little observation. Again, I didn't think of this. Somebody showed me, I'm showing you, right? We all benefit from whoever was the first clever person to think this through. But I know that I can find points on each of these planes. I know I can subtract them to give me a vector like this. And lo and behold, that vector's component in the orthogonal direction is exactly the distance that I'm looking for. It's just super convenient. How nice. Yep.
What's the difference between like saying the component of AB the n direction versus like AB projected onto that?
I didn't understand. I'm sorry.
Okay, maybe I don't understand.
What?
I was saying, what's the difference between like AB projected onto n and then like AB component n?
Oh, yeah. So component is a scalar, and the projection is a vector.
Okay.
Yeah, the projection is just the only difference is to take a component and turn that into a projection. You just multiply by the little unit vector that points in the direction. In other words, if you want it to be a vector, fine, make it a vector, which you just do by identifying that direction. Is that satisfying? Okay. Yeah. Cool. Yep.
Wait, so in this case, you mean D is a scalar?
D is a scalar. Yeah. That's right. Components are scalars. That's right. Projections are vectors. Yeah. It's just terminology. Yeah. Right. Okay. All right. Okay, here's a really tricky one. Again, I did not think of this one myself. Wish I did. But the clever idea here, two skew lines. Two lines that don't intersect and they're not parallel. In other words, a pair of lines where you have nothing good to say about the pair. Right? They just have nothing in common. A really clever move is to realize that those two lines must be in parallel planes. Oh, whoops. I didn't want to go into pencil mode. Must be in parallel planes. In other words, there is a direction that I can use as my normal vector for those planes, for both of the planes. All that direction has to do is it just needs to be perpendicular to both of the given directions. Again, where have I heard that before, right? It's like, oh yeah, that reminds me of cross product, right? So all you have to do, take the cross product, you can use that as a normal vector to define how you have these two different planes containing these two skew lines. Yes?
How do we know that they're not on the same plane?
That the two lines are not on the same plane? Yeah, we don't. It might be that these are the same plane, in which case the distance would just be 0. Yeah, totally fine. Is that satisfying?
Kind of. Because, how would you be able to differentiate?
Yeah, now, to be fair, it does say skew, and skew suggests, this word skew means that the lines don't intersect, and if the lines were in the same plane, then they would have to intersect. So, you could say that rules this out. But the point is, it doesn't even have to. If the two lines really do intersect each other, you can still define this n vector. You can still find two equations of planes. They'll just be the exact same plane. And if they are the exact same plane, then when you do this, you'll just get 0 as your answer. Yeah. Cool. So, look, the point to all of this is, again, this is just kind of examples of tips and tricks that you can use to solve problems. Again, knowing, this is not a complete enumeration of everything that you could possibly want to know about lines and planes and distances between them and stuff like that. But this is just a bunch of examples of, clever moves that you can incorporate into your own problem solving. Okay. All right. Let's see here now. I got to remind myself where I'm going here. Let's see here. Whoops. Okay, so we did this business, and where are we going next? I guess we're to here now. So we need to talk about parameterizations. We've already talked a little bit about parameterizations. Back to my Math219 notes. So we've already talked about this first part as to what a parameterization is. We haven't seen any examples other than a line, but in general, parameterization generates points. It tells you where to be at any given point in time. So it gives position in space, x, y, z, as functions of... Again, you can think of it as time. You don't have to think of it as time, but we usually do. Okay, so position is a function of time. And again, you can think of that as drawing out the parametric curve. Now, we've seen the line example. Here's a non-line. Let's look at this parameterization. Notice that it gives me position, x and y, as a function of time, or I can think of the coordinates as being functions of time. And specifically, those coordinate functions of time, in this case, are going to be cosine t and sine t. Now, I would like to address the question of how do I then figure out, given this parameterization, what is it? What does it look like? How do you look at a parameterization and decide what it is? And this is another sort of like there is no single way to do it, but there's various ideas that can be useful. Now, in this case, you could strategize and think of it as, well, if I want to know an algebraic relationship between x and y, one way I could do that is to find an algebraic relationship between sine and cosine, because that's what x and y are. And then you realize that, oh yeah, I know a very easy algebraic relationship between sine and cosine, and therefore this is an algebraic relationship between x and y as well. And that means that every point on this parametric curve is on the circle. Does that make sense to everybody? Now, where did I dream that up? How did I look at this question and just decide to write down that equation? Well, I pulled it out of thin air, right? But it was it's just the only thing that occurred to me and happened to be very useful. So this is the kind of the insight part of it. The good news is this particular parameterization comes up a lot, right? And now you don't have to think creatively about how to decide what this equation is. I already showed you, right? So going forward, when you see this parameterization, you can immediately just realize, oh, well, that's clearly that's parameterization of the unit circle. Right? And then if you see something kind of like this, I'm going to make a geometric appeal, or let's say, an intuitive appeal. If I were to put a k in front of each of these, well, it wouldn't satisfy this equation anymore. You can probably see how I can adapt this. I can adapt this by just turning this into k squared. And now it works again. And so this is a parameterization of a different circle. Everybody see what I'm talking about? Okay. All right. Alrighty. Now, what am I going to do with this parameterization? What is that? Well, there's different ways that you can approach this. Actually, there's really several ways that you can approach this. I'm going to show you two of them, and this is not the complete list. Just different ways of thinking. What I can do is I can solve for t in one of the equations. I can then plug that in into there in a different equation. And don't forget what these equations mean. This is a formula telling me what y is, and so that means that y must be, you just kind of multiply it all out and collect everything together, and notice here's that green, t is x plus 1, right? That's just plugging that in. And lo and behold, I have a relationship between x and y. Right? So this strategy of solving for t in one of the coordinates and plugging it into the other coordinate can be very handy and results in a very satisfying answer here that clearly this is a line. Is everybody happy with that? Now there's a weakness in this strategy. I had to be able to solve for t. Now that was easy here. But what if it was a weirder formula, right? And I just I can't solve for t, or if I do, what if I end up with over here I'd have arc cosine? Nah, nobody wants to play with arc cosine, right? So if you either can't or don't want to solve for t, then what do? Well, now again, you got a lot of options, but here's one that works nicely here. We can try to form an explicit relationship between x and y by simply trying to notice a relationship. Trying to notice a relationship between the formulas for x and y. And right off the bat, one thing I instantly notice about these two formulas is, well, they're structurally really similar. They're both a multiple of t plus a constant. Structurally, they're really very, very similar. And so, without too much trouble, I'll bet you I could start tweaking x and turn it into y. And just keep track of what you're doing as you go along. So here's that process. You'll notice all I've done there is multiply by 3. All I've done here, is add 7. In the process, though, I've taken the formula for x, I've produced the formula for y, and so as I've done this to the formulas, again, just keep track by being legal with your algebra, keep track of what you're doing to x, and the punchline is a relationship between x and y. Same as we got before, right? Good news. But very different approach. And notice in this strategy, I did not have to solve for t. And sometimes that's essential. Okay. All right. Okay, here's a tough one. On to 3 dimensions. What do I do with this? Can I find an obvious algebraic relationship between x, y, and z all together? It's not clear how you do that. Right? So the neat move here, and again, this is just tools for your toolbox, right? I'm not expecting that you would divine this on your own, right? But I'm going to show you how this idea can be useful in this case, and then you get to copycat it in other circumstances as may arise. Here's the neat move. Let's first think about what happens if I ignore z. I'm going to look just at the x and y coordinate. We'll deal with z later. For the moment, let's just think just about x and y. In other words, I'm looking at the shadow. You might call the projection in the xy plane. And that shadow, cosine and sine, I recognize that. That's a circle going around like this. Previously noted. So whatever this curve is I'm trying to find, I know what its projection to the xy plane looks like. All right, now let's think through what's the projection to the z-axis. What's happening? Just z, ignore x and y. What's happening with just z? Oh, well, that's an easy one. Z is just rising at a constant rate. There's the formula, it's t. Z equals t. So now, still don't know what the curve is, but I know that these projections that I describe are doing like this. So as the shadow in the xy plane is going around in a circle like so, the height is rising at a constant rate. Right now, again, huge geometric appeal. Right, you got to be able to think, put these puzzle pieces together. But if the shadow is doing this and the height is just right, this is harder than it looks, by the way. So circular projection and the height rising at a constant rate, you can just kind of piece together that that's a helix. Very geometric leaning argument, but again, looking at one piece at a time, I can kind of assemble this inference that this is a helix. Everybody see the idea there? It's a tricky argument. Again, I wish I'd thought of it. I didn't. Somebody showed this to me, but it's very handy. When it's handy. This is how often is this exact trick going to come up? I don't know, here and there, but it's, again, good to have tools in your toolbox. Okay. Alrighty. Stopping there. Back to the Math212 notes. Sorry, this is elsewhere in the 219 notes. Reminder, we're doing a lot of bouncing around today. I think this is a good approach for given what we're doing. The very first thing I need to do is scratch out this stuff right here. I'll remind you, Math219 is a different course. It assumes students are good with linear algebra, which this course does not. So we have no expectation that you've seen any linear algebra before. Right? And what I just scratched out is kind of a neat thing that you can do with the derivatives in linear algebra, but it got nothing to do with us. So what I want to ask is, suppose we have a parametric curve. So we've talked about parametric curves just now, right? Position as a function of time. And suppose I want to take a derivative of it, whatever that means. Right? Now, y'all remember the formula for a derivative. I'm going to write this down here, just kind of hoping it'll make sense. I don't know. We've never applied. You've never applied this construction called a derivative to a vector-valued function like a parametric curve before. So that's a brand new application. We don't really know what this is going to do because we've never applied this construction to this kind of an object before. But if we're going to talk about derivatives of a parametric curves, it kind of feels like this. I don't know. It feels like it ought to be this. So let's try it. Let's see what happens. Let's make geometric inferences. Let's just draw out the picture and see what this would mean if we decided to call this the derivative of a parametric curve. And so here we go. Fingers crossed. And let's see here. So we're going to look at the position that we're at some time t. We're going to look at the position that we're at h seconds later. So, we're a little further away down the curve. Now, then we're going to look at the difference of those. The difference then gives me this vector. So my numerator is a vector like that. Everybody happy? Notice that vector is what you might recall from in single variable calculus. They talked about secant lines, right? So since this is a very similar picture, I'm going to call that a secant vector to the parametric curve. It's not tangent, but it's in the limit as these things get closer and closer, it would approach tangent. So thus, anyway, the term is secant curve. Okay, now we're going to take this thing and divide by h. So h being some value, whatever the time difference is between these. When you divide by h, you're going to get a vector that points in the same direction, but with a different magnitude. Everybody happy so far? So now let's think about what happens when you take the limit. And again, this is just I'm going to make a hand-waving geometric appeal. We're not going to be rigorous about all the details, and let's not worry about differentiability and all the regularity formalities, stuff that in practice we're not going to have much of a use for. What do you expect to happen as h gets smaller and smaller? Well, two things are going to happen. On the one hand, those points are going to get closer and closer and closer. Your numerator is going to become shorter and shorter and shorter. But then you're also dividing by a smaller and smaller h. And those kind of, as your difference vector gets shorter, as the h that you're dividing by gets smaller, typically you would expect that those kind of competing forces would balance each other. But the other thing that happens, and now I'm going to erase all of these things here. The other thing that happens in the limit is that the direction defined by these differences gets closer and closer to being a tangent line. And in the limit, geometric appeal, not going to prove anything about this. In the limit, we expect it to be tangent to the curve, not just secant to the curve. Does that kind of seem believable? Yeah. So, altogether then, this thing that we've written down here, that derivative of a parametric curve, we expect to be a vector that is tangent to the curve. In other words, we expect it to be pointing in the direction that the curve is going. Believable? Okay. All right. The other thing, let's take the magnitude of the derivative. Magnitude, right? I'm going to take the vector magnitude there, which means take the vector magnitude here. Now I'm about to commit a little math crime, but this is a math crime that I'm going to claim is actually okay in this circumstance, and I don't want to get bogged down in formalities, so apologies. But in this case, we can bring that inside of the limit. And there are some issues to be worried about there, but if I just take the magnitudes on the inside instead of the outside, in this case, as long as everything's fine with the x function and nothing particularly bad is going on, this works just fine. And so if you think about it then, the magnitude that we're interested in, why did I erase these? I need to keep that there. That magnitude, notice, becomes a distance divided by an elapsed time. Distance per unit time. Where have we heard that before? That's speed. Right? So the magnitude of the velocity. Excuse me, I'm sorry, I got ahead of myself. The magnitude of the derivative is the speed. So, is everybody happy with that before I... Okay, so putting these two observations together is where we get our nice conclusion. And that is that this thing that I'm trying to understand, this derivative vector, points in the direction of motion whose magnitude is equal to the speed. And that is the very definition of what we call the velocity vector. That's exactly how the velocity is defined. Velocity is a vector that points in the direction you're going and where we use speed as the magnitude. So, wonderful little interpretation then. The derivative of a parametric curve is a velocity of the parametric curve. And then you can make an analogous argument that the second derivative is the acceleration. And this is in a physics class. I don't want to get, let's not, but I think that's pretty believable, I hope. Second derivative acceleration. Okay, so cool facts. Here's an example of how we can make use of this. Let's suppose that you have some particle moving around in space, and suppose you don't know what the position is. Suppose we just know that the velocity is given by this formula, and that at a particular moment, let's say when t equals 0, we know that we're at that location. So the question is going to be to conclude other things about this particle. First, we're going to find what is the acceleration of the particle, and then we're going to find what is the position of the particle. So now y'all may remember questions like this from single variable calculus, and it's just derivatives and antiderivatives, basically. So the first part is very straight up. We've, on the previous page, noted that acceleration is the derivative of velocity. So recopying from the previous page and plugging in what we're given about the velocity, I can just straight up take derivatives and compute that that's the acceleration. Everybody see what happened? Okay, now going the other way. I know that velocity is the derivative of position, but if I turn that around backwards, position then is the antiderivative of velocity, right? Okay, position is the antiderivative of velocity. Okay, so we can write that down. And here we go. Position is the antiderivative of velocity. Again, velocity given. Right? Good news, again, that I don't want to get bogged down in, but if you're taking either a derivative or an antiderivative of a vector-valued function, you just do it one component at a time. It's exactly what you would hope and exactly what you would think. These are a couple of antiderivatives that I can just crank out. Let's take this opportunity for me to remind you, I am going to assume in this course that you're proficient with antiderivatives and derivatives as well, right? So make sure you're good with all of the, like the chain rule and the product rule for derivatives. And then for antiderivatives, make sure you're good with all the standard antiderivatives, but then substitutions, there's a bazillion of those. Integration by parts, which I personally believe should be called anti-differentiation by parts, but I'll let that go. And various, little quickie, little easy kinds of make sure you remember how to undo standard derivatives. Like the derivative of tangent is secant squared. That means that the antiderivative of secant squared is tangent, right? So that kind of, all the little sort of standard cases. Okay. All right, so antiderivatives, this. And don't forget to say plus C, and y'all remember the whole deal with that, right? Now here, you could think of it as that we have a plus C, I wanted the pencil here. Think of it as we have a plus C1 there and a plus C2 here, and really all I'm doing is taking the C1 and the C2 and just kind of rewriting them as a single vector C. So this is really just a byproduct of old single variable calculus. And the question then is, how do I compute what that C is? And I want to start by dispelling a myth. There is a shockingly pervasive myth that C is always the initial value. And that is false. It's not even close to true. It's also completely illegitimate reasoning. And of course, that's the more important point. So you're going to see now in this example that what I'm claiming is the case, and that our C that we're about to solve for is not the initial value. Right? We have to go through a process to find what the C is. The way we do that is going to involve using the initial value, but it's not the same thing. The big idea is I'm going to plug in t equals 0 into the existing equation, right? So I already have, colors. I already have that stylus, that x is that. I'm going to take t equals 0 and plug it in to there and to there and see what happens. And when I do so, plugging in t equals 0, let's see here, x at t equals 0 is that. This expression here at t equals 0 is that. And C that we're trying to solve for, I don't know what that is, but let me just recopy that down, right? So all I've done here now to get to this equation, I've taken the previous green equation, I've just plugged in t equals 0 and seen what comes out. So having done that, I can then look at this equation, and it's pretty straight up to solve for C, right? I mean, no big deal. Here it is. C is 2, 5. And notice it's not the initial value. All right, now, having noted this, and I have hope that I've dispelled that myth, let me tell you my theory on where this myth comes from. My theory is that there's a lot of high school calculus classes out there. Whoa, what did I just do? Somehow did I Okay, yeah, here we go. I think there's a lot of high school calculus classes out there where the only functions that they ever write down are polynomials. Well, if you take an antiderivative of a polynomial, you get another polynomial. But, in particular, you get a polynomial where every term in the polynomial has at least one factor of t. And if every term has a factor of t and then you plug in t equals 0, everything goes to 0. And so this whole thing here, just the whole thing turns into 0. In which case, in, such a, arbitrary circumstance, then yeah, the constant does end up being exactly equal to the initial value. But that's a coincidence. It's a coincidence that hinges on this arbitrary and completely unrealistic over-reliance on polynomials that high schools tend to do. Right? So, anyway, just be aware of that landmine. It's real easy to mess that up. And I emphasize, the problem here is not that you will get a wrong answer. The problem is that if you misunderstand this, your reasoning will be illegitimate. It's not a matter of the answer. It's all about the reasoning. And of course, y'all read my multiple blurbs on the website about how important that is and how that's. And then, of course, I talked about this in the organizational video. This course is fundamentally about valid reasoning, not about answers. Okay. All right. Cool. Let's see here. Real quick. This is neat facts. Ignore all this stuff. Again, this is a reference in the Math219 textbook. You don't need to worry about that. And in our textbook, this is not called Proposition 1.4. Nevertheless, these are some pretty cool facts I want you all to be aware of. If you take a derivative of a dot product, there is a product rule that's exactly what you would hope. And if you take the derivative of a cross product, there is a product rule that is exactly what you would hope. So it's really nice how that works out. And so good news. Do make sure that you know these results. And if you're curious and highly motivated, you could even work it out. It's just a matter of computing both sides by coordinates and just cranking it out. There's nothing really particularly tricky about that. Okay. All right, so now moving along. Couple of things to say about arc length. If you want to compute the length of a parametric curve, some really nice ideas that come up, and let me remind you of some things we've already done. We've talked about the derivative vector, x prime. Right, x prime, the derivative vector is some vector that it's the velocity, right? It's something like that. It's tangent to the curve, right? And the magnitude is equal to the speed and all that business. Okay. So, the very first thing I want to define is this thing called the dx vector. The dx vector is what we call a differential. A differential, you may recall from Calc 1 class, a differential is a linear estimate of change. Right? So if we're moving with a certain velocity, then in some amount of time dt, if I know what the velocity is, then in some amount of time dt, velocity times time should give me that estimated displacement, the estimated change in position, and that's what we call the dx vector. So sometimes this is called the position differential because it's literally a differential of our position. How are we doing with that? Is that believable? Okay. And of course, alternately, v dt because x prime is v. Okay. All right. Now, another little detail I'm going to throw out there. Before I do that though, let me make the observation about this little piece of arc length. How long is this little piece of curve? Geometric appeal. If I have an estimate of how much my position has changed, right? The dx vector tells me I was here and I think I'm about here now. If I just kind of assume that displacement, and in a differential when dt is small, you would expect you've moved pretty much in a straight line. The distance that you've moved, you would estimate to be just the magnitude of that displacement. So, magnitude of the dx vector. Sorry, wrong color. The ds should be the magnitude of the dx vector. Does everybody believe that from the picture? Seems kind of plausible. Yeah. Okay. All right. Okay, so what's this business about t, and what is this business about TDS? This is a really useful object that we're going to talk about quite a bit. It's the unit vector pointing in the direction of the velocity. So it's very simply, it's the velocity divided by the magnitude of the velocity. Unit vector pointing in the given direction. Old formula from like first day of class, right? Oh yeah, question. You're good? Okay, yeah. If that's what that is, if you take this formula, let's see now, how do I do this? Let's take this formula for t, and let's take this formula for ds, right? And let's take this formula for the dx vector, and if you put it all together, the magnitude of x prime cancels, and we get this nice convenient relationship that we have an alternative formula for the dx vector. You can think of the dx vector as being x prime dt, but you can also think of it as being t times ds. Now you can think of that algebraically like I just showed you, or you can also just think of this as a looks like a duck, quacks like a duck situation. So let's think about TDS. What direction does that point? Well, it points in the exact same direction as dx. What's its magnitude? It's the magnitude of this thing is ds. It's got the same magnitude as dx. So this expression here, TDS, has the same direction as dx. It has the same magnitude as dx. It looks like a duck and quacks like a duck. So it's a duck. Right? That is just kind of a geometric appeal, but I find that satisfying. A little bit less algebraic, but very satisfying. Okay, and I'm out of time. I'm sorry. We were a little bit over. We will pick up right here next time. See y'all later. Yes?
For the helix example,
Yeah.
it matters if it's radian or degree.
It doesn't matter what?
If it's radian or degree.
Yeah. In this course, we will always assume radians unless it's explicitly indicated otherwise. Radians is overwhelmingly the most natural way to talk about sine and cosine. Degrees are really a very arbitrary, made-up units. Basically, don't ever give me degrees unless the question explicitly asks for degrees. Yeah. Is that cool?
Yeah.
Yeah. Cool.